Get it
Does
for
she
that.
not have her shoe?
It's a flip flop.
Does she not have her shoe?
What do you mean?
Well, she was wearing it.
I just took her flip flop off of her foot and threw it out the window.
So now next slide. You said you explained how you get better at grad school. What's that better at grad school?
When? Oh, look, we started the video already. We don't have one.
LLC, come on, go.
Well, I so we don't have
Not that complicated. When I was in grad school, as grad students, you make money. You don't make much. So I came up with a bright idea. I happen to be a deal connoisseur, as some of you know. And this is back when I was still in the PCs, believe it or not. There was a time when that was true. And I found online these deals that you could buy Dell computers for hundreds of dollars off. So I came up with the bright idea to start selling them on eBay for profit. Not a lot, but on each computer you could, if you're selling fancy nice computers for, I don't know, $700 or something like that, there's a profit of maybe $100 to be made per computer. A lot of times they'll have $50 because after you pay eBay fees, pay whatever. The only way to actually make it profitable was A, to make a company, B, to buy in large bulk. So they did this. Well, the problem was I was a grad student, and obviously I was taking classes and doing all these other things. I didn't exactly there's nobody at home in my apartment to sign for this. So I thought, why not just have it shipped to our mailroom? So what's happening periodically is every 2 weeks, something like 34 boxes would stack up of all the computers and monitors and everything I bought. Well, the dean of the engineering department found out about this and was less than thrilled. In any case, besides threatening to throw me out of grad school if he saw another box that was there for personal use, he went on this spiel about how that's use of government money because we were a land-grant school and how I was abusing the system. This is a whole bunch of bullshit. They just told me not to do it anyway.
So wait, you're using school funding to buy the computers in the first place?
No, I wasn't using school funding. I was using the mailroom and all the resources of them to deliver the packages. I didn't think it was that big of a deal. I thought someone was just going to yell at me or say, don't do that, and that'd be the end of it. I didn't expect to be expedited to the dean's office and sit there to have him saying, I'm pretty sure he was serious, that if he saw another box that wasn't for school use, then I would be thrown out of school immediately. So,
At least you made some money?
a little bit, yeah. I think we only ran it for, I was doing that for about 6 months or something like that. I didn't make a ton of money.
34 boxes every 2 weeks, $50 a box, that's a lot of boxes.
Yeah, I remember.
1,700.
So I probably, I might have matched my salary, so I might have made, you know, 4,000 or 5,000 in that amount of time, because every apartment made about the same. Something like that. It wasn't a ton of money, but.
That's still a good amount.
Yeah, when you're only making, because in grad school, I only made like 15 grand, I think, so it was a good chunk of money. Probably. Okay, so today we're going to move on to more of chapter 4. Just looking at the timeline, we only have a little bit more of a month of school. So I think what we will do, I think trying to fit 3 more exams in the amount of time we have is not going to be reasonable. I'm also slightly concerned as to whether or not we're actually going to get into chapter 7. I wish I would have looked at that before I started today. I might start to skip some topics. For those of you that are going to take Hamilton's course, you'll pick right up in chapter 7, so it's not that big of a deal. So I think we'll try to maybe have an exam after 4. Okay, so then it's only 3 and 4. We'll know in about a week whether or not it's and then your final exam should only be over chapters 5 and 6 most likely, whatever little bit we get into 7. So you'll have a homework assignment today that is also based on just more computational problems. We'll try to kind of stick.
So the final's not comprehensive?
The final is comprehensive.
You said the final's over 5, 6.
But your final test, sorry. Yeah, I didn't put that.
Okay.
I said your final exam. And what
I
I meant by
just
that
got my
was
hopes up so
your
high.
third exam.
You do Ben, don't you Ben?
Okay, but you always have the option to. All right, so where do we leave off? I believe we left off sometime last time. We were talking about Bragg law. Okay. And actually, your homework, your first 2 problems are over Bragg law. I didn't do the homework assignment last time. So now we are going to start with properties of matter waves. Properties of matter waves. All right, what is a wave? What things denote a wave? There are some simple things. Alright, give me something that denotes a wave. Wavelength, most obvious one.
Trials.
What'd you say?
Trials.
Sort of. That's like, it's shape. There's another word for that actually I would take. Amplitude. Okay, amplitude's got to go up and down, up and down. So,
A function.
yeah, but it's more specifically, it has to be
Wavelength. Frequency.
amplitude. And all the ones that we deal with are usually sinusoidal, which of course, cosine waves are also sinusoidal. Sine just won that one. What else? What else we got? Frequency. Frequency, there we go. Okay, it's one thing. These two more or less define the shape. This one defines, period. What else? What else? Yeah, how fast? What would a term for that be? The book also mentions speed. Okay, now I don't want to write speed up here, so I'm going to disagree with the book here slightly. Because speed is actually over-defining your wave. Between these two right here, we can get the speed of, I'm sorry, not those two. This one, this one. We get the speed from the wavelength and frequency. Right. If you actually define a frequency, a wavelength, and a speed the wave is traveling, you run the risk of over-defining your wave, and you might have it wrong. That's like defining the mass, velocity, and momentum of an object. You can't do that. You can only define two of them, and those two define the third. All right, so we're going to do in 2212. The course. Oh, not here. All right, we came up with a wave function. And that's what we're going to work on today. We came up with a wave function that described this behavior. And we dealt with simple waves on a string. We dealt with sound waves. We even dealt with light waves. Now, for this, we said that the wave function is what determines the amplitude of the wave as a function of time and position. Now, it was kind of neat. It was the first time that we had some sort of wave equation, and we can call it, sometimes we called it y or a, x of t, amplitude x of t, or we call it the displacement x of t. We had lots of different words for it, but it was a two variable function. Okay, as a function of time and position, you can figure out what the amplitude is at any given time. All right, in electromagnetic plane waves, you know what, everyone's here. We don't necessarily have to film this, unless you guys actually go back and watch these, which, do you?
I
Every
did
night before I go to
once
sleep.
or twice.
It's a little scary.
I do.
Okay. Well, you know, it's not a big deal. Electromagnetic plane waves. All right, electromagnetic plane waves make things slightly more complicated. We need two different functions. We need E, x of t, and we need B, x of t. Right? This is going to describe the electromagnetic, well, both. We've got the electric field that's oscillating and the magnetic field that's oscillating. If you want to take my 4000 course, we'll go into great detail about
Teach
that.
me next semester?
No, unfortunately not. Theory I'm supposed to teach it next fall, but I have a feeling I'll end up teaching this course again. I think there's going to be more demand for it. All right, so we've got electric here, and we've got magnetic. All right, now, this idea of matter waves, things of actual matter, of actual substance, we have a different equation, and we're going to do it as the psi function. So for you P-comers, this is where the course starts to get a lot easier.
Yeah.
Psi function, sorry, what would be the word for this? What do we call this?
Wave function?
The wave function. It's most commonly known as the wave function. Another way to describe it, though, right now, I want to put it as probability what?
Wait, the probability of anything being at any one particular point?
The probability amplitude. Probability amplitude. Now, we're going to talk about something that is the probability function here in a little while, or probability density. What's the difference between the probability amplitude and the probability density? Barry, remember? Psi squared. Psi squared is, because you're the only one who actually finished. Gotcha. Probability density. Psi squared. All right. Yeah, I keep thinking there's a bunch of you that went through that.
Well, we went there, we just didn't finish.
There you go. All right. Now, as of right now, we're going to call it either the probability amplitude, or more importantly, we're just going to call it the wave function. Now, Jared, David, did you guys get to the point that you were dealing with these sides?
I was showing the equation and all that.
Okay. All right. Fair enough. Okay. So now, when is this useful? How is this useful? Let's go back.
Yeah, because I think it's like, I think Schrodinger is like week 2 for us.
The year. We're going to hit Schrodinger. What day is it? Today's Tuesday. It's right away my soul. We're going to hit the Schrodinger equation on Thursday. I stopped just short of it because I didn't want to go into that because it's heavy very fast. The year 1924. The man, Louis de Broglie. Cool guy. And he's not German for once. We have a Frenchman. Yeah. Frenchman came up with the idea. He postulated, crazy postulate, that particles, things that have mass, have a wavelength that is given by Planck's constant divided by the momentum of whatever that particle might be. Now, this isn't really that, revolutionary from our point of view. He goes, here, I have an equation. This denotes the wavelength of matter. And everyone says, well, wait a minute, this exact same equation already exists. We've already used this equation to say that this is the wavelength of a photon. To figure out the wavelength of electromagnetic radiation, we figure out whatever the momentum of that is, the momentum of the photon, and just take Planck's constant divided by that, we get this. He says, yes, it's the same thing for matter. And it only took 5 years. So by 1929, everyone had firmly proven this using things like electron refraction that we were talking about before, with the crystalline structures, Bragg theory, and all the rest of this, to say, yeah, it looks like that this is really true, that matter actually has wavelengths. So 1929, Mr. de Broglie, and I don't know if I'm saying that right, wins the Nobel Prize. This is actually pretty remarkable that he says this in 1924, and within 5 years they were able to prove this. If you remember, when did Einstein get his Nobel Prize?
Like 27 years later?
No, just a couple years later. I do believe it was 1931. So it took a long time. He came up with the basis for all of this stuff back in 1905, and it took him a long time to really earn his Nobel Prize. And he ended up winning it for general relativity, I think. It wasn't even E equals mc squared. I believe. Okay, so he's saying that all matter has a wavelength no matter what. Let's take a look at what this would mean if he is in fact true. And since he won the Nobel Prize, we're going to go ahead and assume that he is true, that he is correct. Alright. Now, let's go through example 4.1. Example 4.1 says, alright, all matter has this wavelength. So let's take a look at a couple examples of these wavelengths. Let's look at an electron, and let's look at a plane. A. Let's assume an electron is moving at 900 meters per second. What is its wavelength going to be? Well, the very first thing we have to do is calculate its momentum. We need to know its momentum. Wavelength of electron is going to be h over its momentum. What is the momentum of an electron?
It's mass times speed.
Yeah, but why? Why can't I just use NV out of this? And how do I know whether or not I can use NV out of this? What lesson did we learn from our last test? What?
You don't want to listen to that test.
We always listen to electrons. That
what? No,
It's not massless.
What? It's not massless, no. But the point being is that whether particles are massed or massless, we have two choices whenever we want to talk about momentum or energy, and we have to say, do we take into relativistic concerns? Okay. For the rest of the course, you have to keep in mind that relativity is still a possibility depending on how fast we're going. So, you are correct that we're just going to use mass times velocity because we're only moving a mere 900 meters per second, which might sound fast, but in terms of relativity, is nowhere near the speed of light. So until you get close to 1% the speed of light, remember that's where we kind of take our limit, we don't even bother to consider relativistic effects. So this electron, we can take just classical momentum. 6.63 times 10 to the minus 34 joule seconds, all divided by the mass of the electron, which is what? Brad, what's the mass of the electron?
10 to the negative 34. Or 31st.
31st. You guys are all going to put in class, and that's the one thing you're going to remember somehow.
What is it?
It's actually sticking now.
What is that?
Oh, I thought you were being an ass. I said you're going to come out of class, and that's the one thing that you're going to remember. I don't remember anything else, but I know the mass of the electron.
I remember to tell people not to take this class.
Oh,
It was like,
Yeah, that helps a lot.
no. Practice is
All right.
Wait till after you take the classes.
Say it again? Wait till after class to say that?
Like after he's done with the class. He still has control over that, right?
Well, my grade doesn't really need much controlling at this point.
8.1 times 10 to the minus 7th, which is actually 810 nanometers. This is kind of large. This is a very large wavelength. In theory, we could see this, or we would actually have to speed up for us to slow to see this. This wavelength is quite large. All right, so let's take a look at a plane B. How big did they say the plane was? 25,000 kilogram plane. What do we get for a wavelength of the plane? It's going to be h over momentum. First of all, we're assuming that the plane is going to be moving the same speed, 900 meters per second. How fast is that in miles per hour, approximately? Do you remember how to do the conversion?
For 1 meter was 3.14 feet.
Right, but the easier conversion, and I always try to tell my intro students this, is just double it. When you're from meters per second, you can double it, and you get the approximate miles per hour. It helps you know. To be specific, this one is just over 2,000 miles per hour.
Which is kind of slow.
For a plane,
Oh, for a plane, sorry. Yes.
2,000 miles per hour
No.
is kind of fast
yeah.
for a plane.
Talking in special relativity or not?
Yeah.
No, we're not.
I mean, I've seen planes that do like 0.1 speed of light.
Yeah, I've learned a
What
lot.
is the fastest air-breathing plane ever?
Mach 5.
It's the SR-71. Let's check the record in what year? 76. It's been a long time. Nobody's done anything in 76.
And they've started up higher, too.
Yeah, the SR-71 ones are. And, well, they became Decepticons. But in any case, what was that speed?
11.8.
What?
11.8.
11.8 what?
I feel like it was 11.8 times the speed of sound.
That could be Mach 11.
Well,
Well, in miles per hour, it's almost exactly this. It's 2,100 miles per hour. So I don't know if the book intended for that when it picked this problem, but 900 meters per second is almost exactly the record for the fastest plane that we know of. We're not talking, not fastest space plane. What am I trying to say?
Spaceship?
Spaceship. I couldn't come up with spaceship.
Space
Plane. That is not what I want to say here. Space plane. All right, spaceship, yes. So 25,000 kilogram plane, moving at 900 meters per second, we get 6.63 times 10 to the minus 34 joules per second. Now we divide by the momentum, and we're going to say that this is moving at 900 meters per second, multiplied by the 25,000 kilograms, and we get a wavelength equal to 2.9 times 10 to the minus 41 meters. This is the wavelength of airplane. Okay. This is 25 orders of magnitude smaller than the nucleus of an atom. So ridiculously small. So the wavelength of a plane is so small that it is inconsequential. The plane will obviously act just like a particle. But here's the thing. How can we make the plane act more like a wave? What variable can we change in there? Speed. Speed. We have the plane moving really fast. I mean, 900 meters per second in the scheme of things is not that fast. But what happens as this goes towards 0. The wavelength gets larger. So, although we're saying that even put in 1 meter per second, run that calculation and say that the plane is moving at 1 meter per second. What do I get for a wavelength? All you have to do is divide the 6.63 times 10 to the 934 divided by 25,000. What do you get, Drew?
Still really small.
Stupid small number, right? Okay, so times 10 to, what, 38? So even if you started going down to 0.1 millimeters per second, it's still going to be a large number. That being said, though, as this goes to 0, as the plane starts crawling, or more specifically, as it stops, if it's truly stopped, then all of a sudden, this acts like it's going to act like a very large wave. How do we fix that? We want to say that massive objects, macroscopic objects of large mass, decent size, all of a sudden will have a wave as soon as it stops. So if I just stop moving, I'm going to have a wave nature. And the wave could be arguably large because we're dividing by 0. Anybody want to foreshadow the solution to this?
Because in the scheme of things, it's such a small percentage that it just kind of cancels out, or it becomes unrelative.
No, it's not that it's a small percentage. In fact, it could be very large. Let's say that if you're standing still, I could say that I'm moving at 1 times 10 to the minus 38 meters per second, because I'm not moving at all. Okay, that would give me a large wavelength, like a wavelength of a meter of as an existent particle. What it comes down to is the fact that define not moving. Turns out not moving is not moving as we think it is.
Wait.
Not moving. Cup is not moving.
Relativity.
Define that.
It's not moving relative to the table.
No velocity relative to the table. Maybe, maybe not. At the atomic level, we start looking at this. The atoms are moving. This is moving back and forth within its own space. Okay. Now, you say not moving because I want to pin this down. I want to say this has one location it is not moving. What happens if I try to pin down that location? Why? What am I hinting at?
From this scale, it looks like it's not moving. Is that what we're going for?
Well, from this scale, right. So then you go down to the molecular level, and the atoms are moving back and forth, and they have enough of a velocity to overcome this to say we have a wavelength.
The exact location.
Why? What physics says that you can't? What's that fancy thing that we haven't got to that's later in this chapter? Uncertainty principle. So the idea is I want to say that that cup is not moving. It's sitting right here. It has an exact position. It has no velocity. If I start to zoom in on that cup, I'm going to find out I'm lying. That cup has an uncertainty in its position. It is moving ever so slightly because all the atoms are moving ever so slightly. So what am I defining as the cup? Just one of the atoms? No, the whole cup is one atom. It's a collection of things. So there's an uncertainty as to what I want to say this macroscopically is. So it is actually moving back and forth. It is vibrating back and forth. Not like the Flash. You can't go through walls though. That is cool. Okay, so we'll get to that. But the point being is that's how this fixes. And it doesn't have to move much, just the tiniest little bit, because if we have any significant mass at all, even a single kilogram, then that number is going to be tiny. A wavelength is going to be inconsequential.
Also, the record is way off. It's like 2.5 Mach.
Wait, say it again?
That's explained. Like 2.5.
Mach 2.5? That's not true.
No.
Really?
I think it is not. I don't know.
Speed of sound is about 340 meters per second. So at 900, yeah, you're right, it would be about 2.5, because it'd be under 3. So the fastest plane can't even do Mach 3? That's some trouble.
Yes, he was.
There's no way it's true.
Yeah. Off somewhere.
Let's Google it.
And we'll figure it out.
So I googled the Mach 1.
It can go Mach 3.2.
What, the SR-71?
The SR-71 Blackbird is the best jet ever built.
So that's
Operate most efficiently at Mach 3.2. I think that means that's the fastest it can go.
okay.
Safely, probably.
Gotcha.
Well, that's like, it has like under that, like it's typical cruising, so that's about as fast as it'll go.
Now, the next thing I want to talk about, okay, is example 4.2. We're not going to go through this one. This one requires some well-being. You're going to have to stare at it. Now, you're going to need this one for your homework, but I don't want to spend what would be the entire rest of the class just trying to go through it slowly. Some of you get it, but some of you wouldn't. You need to read through this one. Hopefully, you read through the other examples that I showed you. Now, example 4.2, we'll read through it though. Suppose a beam of an electron is moving at 3 times 10 to the 6 meters per second, strikes a barrier that has 2 narrow slits. So it's a narrow slit experiment. All right? But using matter, using electrons. Now, the slits are separated by 0.02 microns, and behind which there are electron detectors. So just to get an idea, we've got this double slit here, and we've got electrons that are passing through. Some are going to go through this hole, some are going to go through this hole, some are just going to hit the barrier. All right, at the center detector, which is to say on the other side of here, so we've got detectors all over the place like this that are detecting what's going on. At the center detector, directly in the path the beam would follow if unobstructed. So when I say 2 slits, this is really not the way to think about it. This is to say 2 slits right there and right there in the scheme of things. So this detector is large compared to the slits themselves. All right. At the center detector, directly in the path the beam would have followed if unobstructed, 100 electrons per second are detected, which is to say that the frequency is 100 to the minus 1 hertz. All right. As the detector angle varies, the number of units per time varies in the typical double slit pattern between the maximum of the 100 hertz and the minimum of 0. The first minimum occurrence at detector X at an angle delta X from the center. Okay, so part A, find delta X, and then we can go down there and we can use our double slit equation, which shows you in part A exactly how to figure that out, first minimum. So this is straight out of 2212. How many electrons per second would be detected at the center detector if the slits were blocked? This is part B. All right, you have to cut this off, so you cut 1 slit. Now remember, when you have detectors, what they are detecting is they're detecting intensity, not amplitude of the wave. Okay? So an amplitude function needs to be squared to get intensity, which we're going to get to. Why? When we have the psi function over here, I said that that was the probability amplitude. So if I want to know the probability density, which is equivalent to intensity, I have to square the amplitude function. So in this case, you have to take the square root of your intensity to get back to your amplitude function. So that's part B, so you can read through that. Make sure you understand that. C, how many would be detected per second at the center detector if detector X, if 1 slit were narrowed such that it alone would give a count rate of 36% of its original value. This is the harder one to understand because you're going to go back and forth between amplitude and intensity. You have to take the square root to get down to amplitude, add the amplitudes, and then you're going to end up squaring them to get your intensity back. It's not terribly difficult, it just takes reading, and I honestly think it's going to be better just to read through this one. You will need it in any case to work on your homework. As you'll note from the previous tests, my tests are heavily based on not only just your homework, but on the example problems in the book.
Essentially, which problem does this apply to?
I don't know. Probably,
I'm sure we'll be able to tell.
15, 16. Yeah. All right, onward. So we're going to go through example 4.3 though, because here's a formula that you're going to need. All right, on to example 4.3. So depending on how well you remember the stuff in 2212, you might read through all that and go, I remember this, I remember this, I remember this, and move on. If not, it might take a little bit of review. 4.3 says, all right, we are going to throw an electron through a potential difference, and we want to know when we accelerate it up, what wavelength do we end up with? The whole idea of this problem over here, de Broglie is saying that the wavelengths are dependent on Planck's constant. A constant, nothing else, and the momentum. All right? So the point being is that the wavelength of a particle, whether it has mass or not, is dependent also on how fast it's moving. The faster it's moving, the smaller the wavelength is going to be. So let's figure out what that's going to be just for an electron. All right. So let's say the change in the energy of the system is equal to 0. And we use notation that's consistent with all my intro courses, I should say. I want to know what the potential difference that I have to drive to get an electron of a wavelength. Alright, so what I'm going to assume is that I have no potential or no kinetic energy initial, and all I have is electric potential energy initial, and this is going to go all into kinetic energy final. That is going to be my energy balance equation. I'm going to throw this electron through some potential difference, and I will get some kinetic energy out of it. Now again, we're going to assume that this is not going that fast. Relativistic concerns are not there. So I can say that, just remember, QV is my electric potential energy, and my kinetic energy is 1/2 mv squared. Now, this is slightly confusing, so I'm going to try and cap off my V's here. The large V refers to my potential difference, the small v refers to the velocity of the particle. So, we can simply solve this and say, alright, the potential difference applied of 12 volts, 16 volts, whatever the case might be, will give us an mv squared over 2q. Alright, so given charge, we can figure out that we get this mass velocity complement for this particle. Great, this is still 2212 stuff. Now, let's start applying de Broglie's idea. Now, de Broglie said that this wavelength is going to depend on momentum, so we need to get this thing in terms of momentum. So I can write my kinetic energy equation right here. If momentum is equal to mass times velocity, then I can obviously say p squared is equal to m squared v squared. And another way to write the kinetic energy equation is often written as p squared over 2m. We have to get rid of that extra mass that we left over with. This is a common way in upper level physics just to write kinetic energy is momentum squared over 2m. Alright, so if we put that in here, I'm now going to get I've got p squared over 2mq. Remember the 2 which is still left over from previously. Alright, so then p, I want this in terms of momentum. So I can rearrange this and say that I've got p equals h over my wavelength. In order to put that in here. So if I now shove that in here, I'm going to get a function that is equal to h squared over 2mq wavelength squared. And that's what I want. Now the middle part's not as important. What this is saying is that an electron that's just standing still, if I accelerate it through a certain potential, which is our capital V, I'm going to get this. Alright, what is all this stuff? H, Planck's constant. The mass of the particle and the charge of the particle. Presumably these are constants as well. We're talking about electron, mass of electron, charge of electron. Just by accelerating it through some potential, 12 volts, I don't care what, I now have a function I can tell you exactly what the wavelength of that particle is going to be. Now what's interesting about this is unlike when we're dealing with photons, wavelength is a simple property of the object, and we're seeing that it's usually not changing. We have the frequency of the wavelength of the photon, and it changes. Why do we say that that is an intrinsic property of the photon? Why doesn't a photon go up in wavelength or down in wavelength ever?
Because speed of light doesn't change and wavelength is based on speed.
Right. The wavelength is based on the speed of the object, and the photon is always traveling at the speed of light. Now, it can have a different frequency, different wavelength, but it never changes because it never speeds up or slows down, so it never changes kinetic energy. So, stop.
Or just answer it.
No, I'm good, thanks.
You get time.
All right, so things that have matter, things that have mass, it's a different story. Your wavelength will change. It will change with your kinetic energy, or in this case, it will change with the potential that you follow through. So this is a handy little equation right here. Now, there's no velocity term in here. There's no mass. There's no anything. So it's nice that it's just a direct comparison with the potential that you're accelerating through is proportional to the wavelength that you have.
There is mass in that one.
I'm sorry. You're right. I'm assuming the mass is an intrinsic property of whatever we're doing. Mass is not a changing quantity. Okay. Oh, okay. Let's see. When is this useful? When do we care about this? The fact that particles have wavelength. Can anybody tell me what an SCM is and a TEM? Chemistry, you guys, I assume you would use this.
We probably
You could use it in biology, I guess. SEM, TEM.
Are you talking about STP?
Oh.
Stop reading your book.
I I know.
Not the bars, we're gonna read it.
Yeah, we'll read it out loud. I at least want to see if people can come up with it without always
Scanning.
I'll do that.
scanning electron microscope and transmission electron microscope. Wow, I was gonna say a lot of people. I was gonna say more chemists that I knew used it than anything else, but that was because it was a very applied chemistry type course, or applied chemistry school. In any case, all right, it's a microscope that uses electrons. It's no different than an optical microscope. An optical microscope uses photons. What does it do? It bounces photons off an object, focuses them onto an image, and then that's the image that you look at a macroscopic level. Here's the problem with a photon. Okay, if a photon bounces off something and you want to see it, it is dependent on the wavelength of the photon. Let me try and explain. Let's say a bunch of photons pass off some tiny object like this. Okay, they bounce off of it and they come off at a certain angle, so it determines, I've got all these photons that are coming in, these are bouncing off, all these other ones are passing just by it. Only the ones that bounce off the object are going to actually return the image that you're looking for. Great, so now you've got a screen. So you've got this objective lens that then puts this on a screen or focuses on your eye. Now, these photons are going to go off, and I've got this lens here such that this screen is going to make the same picture a lot larger so you can actually see it, right? And when I say a lot larger, we're talking, 100,000, 200,000 times larger. Great. Here's the problem with that. This is large enough, who cares? The photon comes in here and has its little wavelength when it hits here. The photons started when they bounced off here with their original wavelength. So they bounced off here, here's their wavelength. So it doesn't matter if it's optically visible to the screen like this, it starts off like this. So when it gets here, it has an uncertainty of huge percentage because it's been basically magnified through. So its wavelength isn't magnified, but its uncertainty of this edge has been magnified. Let me see if I can describe that in a different way. Since what you're viewing is
around the edge.
what
You're saying?
blurry everywhere, blurry everywhere. So if your visual, what you can visually see is in between 400 and 700 nanometers, you sure as hell can't look at anything that's anywhere near that size. Because the photon has to bounce off that and come to your eye, and it's going to be oscillating at the same size of the object. So even if you exactly bounced it off of it, well, heck, the edge detection of the photon can only go down to the 400 nanometers. That's as accurate as it possibly can be. Now, as far as blurry goes, that means even if you have something that's a couple magnitude larger, even if you're talking micrometers, the photon's going to have a hard time. Because it's only 3 orders of magnitude higher. So you have, you get to the point where microns is about as small as you can really see. Anything smaller than that, and all of a sudden you're going to say that the wavelength of the object that you're using to see is on the order of 10% the size of what it is. So everything is 10% blurry. My edge is here within 10%. That's why it looks blurry. Does that kind of make sense? So, yes, no?
About as well as anything else in the class makes sense.
Fine.
Okay. So the point being is that if you want to make an image out of something, you have to make an image out of something who has a more particle-like behavior, more billiard ball-like behavior, that it bounces off an object and makes it more discrete and isn't waving all over the place. Now we just learned that all particles, all mass, everything has a wavelength, so we're kind of hosed in that department, but we can win at least if we can use something that has a smaller wavelength, much smaller than the object we're looking at. Electrons. Electron will work out okay for us. Okay, if we're using, we said 900 meters per second here was the speed that we had the electron a second ago. That is a stupid small speed for an electron. Electrons go much higher than that. Once they get to higher, we have very, very small wavelengths. So use an electron scanning microscope, okay, or scanning electron microscope or transmission electron microscope to bounce electrons off objects and then have a detector that then turns that basically that detector into a screen. Because they can bounce off of it, and since the wavelength is so small, the uncertainty is much, much smaller. And we can now view things that are tinier. There is a fundamental optic limit of dealing with photons, and it's just based on their wavelength. You can't see anything that is smaller than the size of them because they're oscillating. You're just looking at photons that are bouncing up and down. You can't obviously see any particles. So that's why you need something smaller. That's an example of, I guess, maybe an example of particles having waves, but why we use particles instead of photons. Okay, what's next? Frequency interference patterns. All right, so let's talk about, we talked about wavelength. So if matter has is wavelength in nature. The three things that we said that it needed necessarily were it has to have a wavelength, it has to have an amplitude, and it has to have a frequency. And the wavelength and the frequency together are going to define its speed. So we've looked at wavelength, let's now look at the frequency. Frequency. All right, interference patterns. So when we had the electrons bouncing off the crystal-like structures, okay, and we created these interference patterns, that's how they knew that, yes, matter does in fact have a wavelength. It's harder to show its frequency. It's much harder. We can say that it has wavelength simply because we have the interference patterns. So it's a little bit more difficult. Let's start with the energy. Energy is equal to hf. We said this was true for photons. Turns out that this still abides. So you get still valid for matter. It's just a little bit more difficult to determine. All right, so we're going to bring back a couple different things. Now, you guys remember uniform circular motion, right?
Of course you do. I remember the term.
All right. We say that some object is going around and around in a circle at a constant linear velocity. I say constant linear velocity, and by that I mean if all of a sudden it was to go off in a straight line, like somebody cut it, we could say that the change in x over change in time that we travel in a straight line is equal to this linear velocity. That's the velocity it's going around in the circle with. Okay, good. Now, how did I turn that into an angular velocity?
With the inertia equation thing?
Yeah, it requires that. An angular velocity refers to the amount of angle that you're traveling through, and change in angle over change in time. What did we call this? Or what was the symbol for this? Yeah, it is. It's omega. Okay. Omega equals the change in theta over change in time. What are the units on this?
Radians per second.
Radians per second. Well, I say radians per second. You don't like that?
You didn't like it.
I can say it.
Well, she's thinking, why do you like it?
Yeah.
Okay. All right, if it's going around the circle once, what's my change in theta going to be? It's all the way around the circle once. What's the change in theta? 2 pi. So I can say omega is going to be equal to 2 pi. What's my change in time going to be going once around the circle?
Whatever you want it to be.
What's the term for it? Amount of time it takes to go around the what? Period. Capital T. Ta-da. So another equation we said for the angular velocity is 2 pi over t. I'm going to introduce a new word, a new definition for this. All right, we were just told, Jared just told me that this is radians per second. But what do we know about radians? Posture unit. It's just there to make us feel better. It's not a real unit. The real units for this are 1 over seconds. What is units for 1 over seconds? Hertz. So now, and most often in advanced physics, omega is known as angular frequency.
What does it sound about?
Because all upper level physics uses it, and we probably used it in 2250.
We did.
We did call it angular frequency?
We had something along those lines.
Okay. We're good.
Well, yeah, it was a multiple choice question. But it was a multiple choice question in 2201 or 2211.
Okay. How do you remember that? I don't know. I mean, I taught that course now twice. I don't remember that. But
I don't know. It's like the first one of like I think it's A1 or 2.
I have the worst memory of anyone I've met that doesn't actually, committed or just or prescribed, I guess. I don't know what anyone said. Diagnosed. That's the other one.
So you're possibly committed. Should be.
Yeah, possibly. We'll see. All right, so angular frequency. I'm going to introduce something new. Okay, wave number, K. Wave number, 2 pi over the wavelength.
So is that K?
Yeah, that is K. It is entirely invented. Kind of the same way that this angular frequency is. So we've got 2 pi over the period. So that's an angular frequency in terms of time. This is known as a spatial frequency. And the whole point of this is in 2 pi radians, we want to know how many wavelengths there approximately are. So we have, in a certain given amount of time, you know, the period, we have this many radians. So in a given amount of, in one wavelength, we have 2 pi radians. The ratio between those gives us our spatial frequency. We're going to use these two things because everything is going to kind of have to cancel. All right, let's go back over here to our energy equation. The original question is, what the heck is frequency? So I can rewrite frequency as frequency equals h over the energy, which may or may not help us. Now, in terms of period, how is frequency and period related?
Inverse?
Yes. So we can say, and I'm writing all over the board in no particular order.
Quick question.
Yeah.
Shouldn't be energy over.
Did I write that the wrong way? Yes. Thank you.
I'm just glad I'm here for this one.
Yeah, there you go. Energy over Planck's constant. Okay, so the other way I can do is I can write T is equal to 1 over the frequency. Perfect. That means the other way to write angular frequency is just equal to 2 pi times the frequency. In fact, I don't really introduce this in 2201, but holy crap, is this an easier way to think about it. What is angular frequency? The angle multiplied by the frequency. 2 pi, the angle, the full way around a circle, multiplied by the linear frequency gives you the angular frequency.
Well, I'm doing great, you did that one.
Because the whole concept of the difference between angular frequency and angular velocity, there are not time to understand what angular velocity is. In fact, we don't even teach the word frequency in 2201. It just doesn't exist.
So you do what you look, right?
In 11.
Okay, so
A lot of words in 11 that are in 12. I have to be very careful with my wording.
A lot of letters.
Okay, so one last thing, and this is slightly obnoxious. Hey, let's just keep filling up random space. This guy.
Oh, I remember that one.
Yeah, what's his name?
Oh, I don't remember what it's called, but I do remember doing that a lot.
A lot. In fact, if anybody had any choice, any physicist or chemist in the world, we would rename this Planck's constant.
Yeah,
So instead, what this is known as H bar. I'm just written literally as H bar, all one word. It just is equal to Planck's constant divided by 2 pi. This is the most useful thing in the world. You will use this everywhere.
Yeah.
Well, for the next month and a half, we're going to use this a lot in this class. How about that?
Okay.
All right. So yes, we'd all like to go back and talk to Planck and say, can you please make this your constant? And then you can just say that H equals 2 pi times your constant. And move that around. Very, very useful stuff. All right, so let's get back over here. Oh, and its value. Might as well write down its value. You can just take 6.63 and divide by 2 pi. But it is equal to 1.055 times 10 to the minus 34 joules per second. And for some reason, I can only have one of these numbers in my head at any given time. I use H bar a lot, so at the beginning of class, this is the one I had memorized. I had to re-memorize 6.63, which I've now been using for 2 months, so I've not forgot this one.
Well, you.
But you really do have the worst one.
Oh, you have no idea. All right, so now what we want to redo is, actually I'm going to erase this here. And I want to rewrite E and momentum in 2 different ways. Okay, so we said that the momentum of an object is equal to h over wavelength. Let's see if we can't rewrite both of these equations. All right, we'll start with E. E equals h frequency, which I can now say, all right, that's 2 pi times h bar times the frequency. Frequency, in terms of angular frequency, we go right over here, we can say frequency is equal to angular frequency divided by 2 pi. So this is going to be 2 pi h bar times omega divided by 2 pi. And look at that, all goes away. Energy can be taken as h bar times your angular frequency, or your angular velocity, whichever term you choose to use. It's nice and handy. It's simple. Okay, now over here. I said that my k is equal to 2 pi over wavelength, or my wavelength is going to be equal to 2 pi over k. So if that's the case, I can sit here and write this is going to be equal to h k over 2 pi. I can then say h is equal to 2 pi h bar, so k divided by 2 pi. Hey look, they cancel again. I end up with h bar k. So momentum. Momentum and energy are very closely related. Momentum is just going to be equal to h bar times your spatial frequency. Whereas energy, turns out, it is your h bar multiplied by your angular frequency. It's kind of a neat trick. Now, if you guys remember, angular momentum is tied very closely to this, and probably went into a great deal of that if you get what I assume.
Sure.
Okay. We'll get there if we get to chapter 7 when we talk about the hydrogen atom.
Oh,
So
yeah.
what is, what scenarios is these equations used for?
Just for dealing with matter waves, nothing we've done here is new. All we're trying to do is find compact ways to describe these things so that when we start working with the equations, they're less ugly. So in what ways we'll use this? We'll simply use this when we're talking about matter that has wavelengths. So as a function of energy and momentum. It's nothing new. There's nothing new. Just a new way to write it. All right, so that is frequency. Now we have frequency we can describe using frequency, both our momentum and our energy. The last one to talk about is speed. Now, speed, in theory, should simply be defined by your wavelength and your frequency.
But it's not right.
That's not true. It is and it isn't. Here, I'll explain.
It's worse.
It's worse.
I mean,
It's so much worse. No. All right. What is the relationship between speed, wavelength, and frequency for a photon?
the wavelength.
No. We already went through this. That's your one answer. You're done. All right.
Simple photon?
Yes.
It's always about the same speed, so.
Okay. So how do we relate those three quantities?
What's your actual wavelength?
Well, that has some meaning, but we'll do the units. What are the units? The way to always remember this, what are the units of, what is the speed of a photon?
8.5.
C, right, which is in meters per second. Wavelength is in meters. Frequency is 1/seconds. So the easiest way is to just look at these. Okay, so C must equal wavelength multiplied by frequency.
That's what you were asking for?
Yeah.
Oh,
Okay.
I said, what is the basic relationship of wavelength, frequency, and the speed of a photon?
Well,
Because it's more
you just-
complicated.
yeah, that sounded a lot more complicated.
Right.
Did you say that? Oh, I thought you said wavelength over frequency.
Oh, maybe I did. I don't know.
Either way, you had the right idea.
Whatever. Okay.
Fine. Now, is this true for matter? Yes and no. First of all, we know that we're not moving at the speed of light, so we have to write this as velocity equals wavelength times frequency.
Do we need the gamma for this?
What?
Do we need gamma for this?
No, well, it depends on whether or not we're going relativistic speeds. We're still assuming that this is not necessarily relativistic speeds. Now, I've got wavelength times frequency. What I want to go do is I want to use this over here. These quantities for energy and momentum. We're going to find out something really interesting as far as the velocity of this goes. So I could say that wavelength here, if I move that around, is going to be h over p. So
Can you define it with
Energy over the momentum.
yes, we're going to see that in a second. Well, we want to use both because we're going to be stuck with h's and we want to get rid of this. So I've got p over h times my frequency, and I just got rid of wavelength using this right here
Why is it P over H?
because it's the inverse of the wave. No, I don't know. I have no idea. I was doing the inverse for absolutely no reason. H frequency over p. Yes. All right. Then frequency I can say is equal to the energy divided by h. So this is going to be h energy over p divided by h. Both of the h's cancel. The velocity is simply equal to the energy divided by the momentum. So again, why are we doing this? Because it allows us to think of things in a different way. The velocity is equal to the energy simply divided by the momentum. All right, let's just think about this in classical terms. All right, if we had that, I would say that this would be equal to 1/2 mass velocity squared divided by mass velocity. All right, what do I get out of that? Well, I would get v over 2. So I'm kind of close. I'm getting the velocity divided by 2 from a classical perspective. So the question is this the velocity of the object? No. This is when we'd end up with the velocity of the object using classical arguments, which are valid, so we're not moving that quickly. So what on earth is this then? No guesses? No. It's the velocity of the wave that contains the particle. This is the reason I like that little video. They're talking about a water wave that holds a dust particle, and the idea is that it's carrying along the dust particle, and we have a description for the wave. We know the dust particle is somewhere in that wave. Okay, the wave is carrying the dust particle, but the dust particle has velocity within the wave. And then when it lands, and even if the wave broke up, you say, okay, I've got 50% of the water over here that was carrying it, 50% over here. There's a probability that the particle's in either location. Okay, if you try and narrow it down, you can narrow it down, but then you're going to lose information about where it could have been, its probability. This is a description of the velocity of the wave itself that is carrying the particle, not specifically the velocity of the particle itself. For that reason, besides the fact that it's terribly confusing, it's also not that very useful in any of the physics we do, so we're not going to use this very much. It's still a valid equation, a valid set of interesting things, but we're specifically generally going to talk about the wavelength, which is nice because we know like it's the wavelength of the thing that's holding the particle, if you will, and the frequency. We'll talk about those more than the velocity itself. All right, we're actually going to get done early today because I don't want to jump into Schrodinger's equation. I want a fresh day to start with that mess. So that'll be Thursday.
I don't like Thursday.
What?
I'm not gonna like doing Thursday.
Well, Schrodinger's equation's not too bad.
Sorry,
we went into a dark
I
room. We
would
went
say that is irrelevant.
Good job.
All right.
So this is a bunch of letters, and letters should be in that. I don't know. So this is the new fall, too. That'd be nice for me. We're fine.
This will probably be in the fall as well, I guess.
I gotta see if we can go back to this.
In the spring, it looks like advanced lab is offered.
Why don't we do away with that class entirely?
Which what?
I think we plan to do away with that class entirely.
I'm not in control of that class. It's Steven's course. And as far as I can tell, you show up anytime you want during the week, and you get to the lab, and you go run it, and that's the whole course. It's 2 credits. It's not terribly difficult. You get to use advanced stuff, probably. I'm not entirely sure what you are going to be using. I don't know if you use a microscope barometer or what stuff you use. But that one's being offered. I do believe that the quantum course is being offered, which is a really good course. I recommend that.
In the fall.
No, this is spring. So those are the 2 upper level courses that are being offered.
Is it?
In the fall, I'm supposed to be offering electrodynamics, but I'm also being pushed to offer modern. There is a chance that I'll offer both. There's also a chance that I'll jump out a window if I have to do that.
Wait, so we're doing the lab in the spring?
Lab in the spring and quantum.
That's a problem for us.
And mechanical.
Okay,
Is it?
do we need?
Okay, I didn't know about that. So classical mechanics is being offered,
I can take this for us to complete the minor.
which is supposed to be a good course. The upper level students said that his classical mechanics was really good.
So I can look that up again.
It'd be nice if they changed to thermo instead. That'd be lovely.
Video.
The problem is, it's not that. The problem is both those courses are offered by Hamilton, both quantum and thermal. And just like I said, I don't want to do